Some stories start with a business plan. Mine starts with an obsession. It's not about the code, it's about this deep seated curiosity for how things really work, right down to the bits and bytes on disk. I'm Alex Gaetano Padula, and I spent the last few years on this journey building TidesDB. And look, this isn't just another key value store. This is a result of 7 major versions and countless experiments, all driven by the desire to build something from the ground up for hardware that we actually use today. The goal was never just be a little bit faster than the industry standard RocksDB. The real mission was to ask, what if we designed a storage engine from scratch, totally optimized for massive parallelism, for modern CPUs, the insane speed of SSDs, and the abundance of RAM? What would that even look like? Well, the answer to the big question starts with tackling one of the trickiest problems in all of software: concurrency. I mean, how do you get all the CPU cores working at the same time without them stepping on each other's toes? The secret sauce in TidesDB is this deep commitment to what's called lock-free concurrency. Instead of traditional locking, where one thread works and all others have to just wait in line, this design uses low-level atomic operations and that lets multiple threads get work done at the exact same time. No waiting. The best way to think about it: a lock-based system is like a group trying to write a document by passing a single keyboard back and forth. It's slow, it's inefficient. A lock-free system, though, that's like everyone editing a Google Doc at the same time. That's the kind of seamless parallelism TidesDB is built for. And the results, do they back it up? Oh yeah. In a sequential write test, TidesDB achieves an absolutely incredible 511% CPU utilization. That means it is using the equivalent of over 6 CPU cores at once. For comparison, RocksDB with its traditional locking topped out at 306%. This right here is the power of a lock-free design in action. But here's the thing: unlocking all those cores is just the beginning. TidesDB's performance actually comes from 3 key architectural decisions, all working together in harmony. These are the 3 pillars. First, separating keys from values. Second, a really smart adaptive compaction strategy. And third, a very intentional trade off to use more memory for a lot more speed. All right, let's start with key value separation. Traditional databases are constantly rewriting both keys and their large values during internal cleanup operations. TidesDB is smarter. It separates them. It only has to manage the small keys in its main structure, and the impact is huge. Scanning through data with large values is over twice as fast. Next up is adaptive compaction. This means TidesDB is constantly adjusting its internal structure based on the actual data you're storing. The result is much lower write amplification. For every byte you write, TidesDB only writes 1.08 bytes to disk, compared to 1.34 for RocksDB. That means less wear on your SSD and better efficiency overall. And finally, the big trade-off. TidesDB intentionally uses more RAM. We're talking over 5 times more in some tests to keep its indexes and filters in memory. Now, why would it do that? To avoid slow disk reads. This is a classic space for time trade, and the payoff is nearly 30% reduction in read latency. We've seen the architecture. Now for the main event, putting TidesDB head to head against the industry standard RocksDB in a series of tough benchmarks. This is where the rubber meets the road. First up, sequential writes, which is sort of the best case scenario for these databases. TidesDB absolutely explodes out of the gate, hitting over 6 million operations per second, leaving RocksDB's 2.36 million far, far behind. That's right, more than 2.5 times faster. This is a direct payoff from that lock-free design, from letting all the CPU cores fire at once. But, but what about a more realistic workload? But what about a more realistic workload? A Zipfian distribution models how real-world traffic works with few hotkeys getting most of the action. And here again, in a mixed read-write test, TidesDB shows a really clear lead and read performance. And check this out. Here's another surprising advantage. Thanks to its adaptive compaction, TidesDB is incredibly space efficient. In this test, the final database was over 5.5 times smaller than the one RocksDB created. Now let's look at seek performance. How quickly can the database find a specific key? Thanks to keeping its indexes, which are compact in memory, TidesDB absolutely flies, hitting nearly 3.5 million seeks per second. I mean, that is a staggering 6 times faster for any application that needs to find a specific data quickly. This is an absolute game-changing performance gain. Now, the benchmark results are pretty impressive, but let's be real, no single tool is perfect for every situation. So based on all this data, how would you choose which engine to use? Well, TidesDB is going to excel in those write-heavy scenarios with hotkey access, especially when you have plenty of RAM and CPU to throw at it. But RocksDB remains the go-to for memory-constrained systems, large batch workloads, and for any situation where its decade of proven, battle-tested maturity is a must. And that brings us to the final question. The story of TidesDB isn't just about one database. It's a case study in designing for the hardware of today, not the constraints of yesterday. It really makes you wonder, in an age where even our phones have multiple cores, is it time we rethought how our foundational software is built?